Hello and welcome to the third lecture in our ECG course. We are going to speak today about the ECG axis because, as we discussed before, that we are going to dedicate a separate lecture for the ECG axis because I know it is one of the difficult points in understanding the ECG. Our ILOs today is to understand the value of determining the axis of the electrical activity of the heart and to learn the three different methods of identifying the axis of ventricular depolarization. First of all, we need to know that we have two axes in the heart, the P-axis, which represent atrial depolarization, and the QRS axis, which represent ventricular depolarization. But when we speak about the ECG axis, we literally mean the QRS axis, but precisely we need to determine whether you are speaking about P-axis or QRS axis because we have two separate axes in the heart. Let's start with the P-axis, which represents the axis of atrial depolarization. Of course, we know this famous diagram which we have seen in the lectures of basics of the ECG, and I want just to emphasize at first, in order for not anyone to be confused today, that when I'm going to say the left upper quadrant or left lower quadrant, let's imagine that you are seeing an image. Because, for example, if you are seeing a patient in front of you, so the right, if you are using, for example, your right hand to show on his heart, so the left side of the heart is at your right hand and the right side of his heart is at your left hand. So don't be confused when I'm speaking about that between 0 and minus 90 degree is the left upper quadrant, from 0 to plus 90 degree is the left lower quadrant, from plus 90 to minus 180 is the right lower quadrant, and from minus 90 to minus 180 is the right upper quadrant. So if we apply the image of the heart here of a normal heart or levocardia, so I know that the SA node is in the right upper quadrant of the heart, so the axis of atrial depolarization is directed towards the left lower quadrant of the heart. So I can expect that the morphology of the P wave, it would be positive in lead 2 AVF plus minus lead 3, and it would be negative in AVR because of course the axis of atrial depolarization is directed towards the positive poles of lead 2 AVF and lead 3 and away from the positive pole of AVR. If you have an image of a dextrocardia in which the heart is reversed like a mirror image, so the SA node lies in the left upper quadrant of the heart. The SA node would not be on the right side of the heart as we expect. So here's the axis of atrial depolarization is directed towards the right lower quadrant of the heart, and so it would be positive in lead 3, biphasic in lead AVR and lead 2 because its axis is perpendicular to these leads, and it would be negative in lead 1 and AVL. If we are speaking about ectopic low atrial rhythm, for example, originating from the crying sinus ostium, at that time, the axis of atrial depolarization is reversed, and so it is directed upward towards the right upper quadrant of the heart, and so I expect that the P wave would be positive in AVR, negative in lead 2, 3, and AVF. So, for example, if I use this ECG as an example, here I see positive P waves in lead 2, 3, and AVF, and negative in AVR, and it is biphasic in V1, so I expect that these P waves are antigrade P waves, and so this rhythm is sinus rhythm as we saw in the image before. And if I use this example here, the P waves are negative in lead 2, 3, and AVF, and positive in AVR, so they are reversed. These are retrograde P waves, and it is low atrial rhythm. So the value of determining the P wave axis is to determine the origin of atrial rhythm, for example, whether it is sinus rhythm, ectopic atrial rhythm, or junction rhythm. And of course, for those who are specialized in cardiac electrophysiology, when they are going to map atrial tachycardia during the ablation procedure, it is important to use the P wave axis in order to determine the origin of the ectopic focus responsible for the atrial tachycardia in order to decide where to start the mapping inside the heart during the procedure. So now we have discussed the P wave axis, so let's speak now about the QRS axis, which represents the axis of ventricular depolarization. Of course, we know that it represents the net overall direction of the heart's electrical activity, and so any abnormality of the axis can hint at ventricular enlargement, abnormal rhythm, or hemiblocks or fascicular blocks, which we are going to speak about this in a separate lecture. Of course, we know this famous diagram representing the three unipolar limb leads, AVR, AVF, AVL, and the three bipolar limb leads, 1, 2, and 3. And if we apply this image here, we can expect the values of each one of these axes, whether normal axis, left axis deviation, right axis deviation, or extreme axis deviation. So for example, normal axis is defined as ranging from minus 30 to plus 90 degree. Left axis deviation is referred to or between minus 30 to minus 90 degree. Right axis deviation is between plus 90 and 180 degrees. Sometimes we may refer to 180 by plus value or minus value. It is not significant. And the extreme axis is between minus 90 to plus 180 degree, would be referred as extreme axis, or sometimes it may be referred to as indeterminate axis. We have three methods in determining the axis of the heart: the Quadrant method, the three-lead method, and Equiphasic method. Let's start with the simplest way, but before this I need to emphasize on an important fact that we use only the limb leads for determining the axis, not the chest lead. We have discussed before that the limb leads look at the heart at a frontal plane, but the chest leads look at the heart at a transverse plane. So the axis of ventricular depolarization would affect the limb leads, not the chest leads. In the Quadrant method, we look at three basic morphology of any limb leads, whether it is predominantly positive or predominantly negative or equiphasic. So we need to see at the net overall direction of the axis, because you may see negative component and positive components in each limb leads. So look at the overall direction, whether it is predominantly positive, predominantly negative, or equiphasic. We would use only two leads in this method, which is lead 1 and lead AVF. If lead 1 is positive, so it is directed towards 0 degree, so I could expect that here is the left half of this circle, which is turned blue, is the direction of the axis of ventricular depolarization. And if lead AVF is as well positive, so it is directed towards the lower half of the circle, towards plus 90 degree, as we expect here. So if I merge these two images together, I would expect that the axis of ventricular depolarization is between 0 to plus 90 degrees, so it is towards the left lower quadrant and it is normal axis. Second example, lead 1 is positive and lead AVF is negative. So here lead AVF is negative, so the axis of ventricular depolarization is directed upwards toward minus 90 degree. So if I merge these two images together, so here I can expect that the axis of the heart is between 0 to minus 30 degree, so it is left axis. The third example, lead 1 is negative, so it is directed away from the positive pole of lead 1. It is directed toward 180 degree, and lead AVF is positive, so it is directed towards plus 90 degree because it is directed towards the positive pole of AVF. If we merge these two images together, the axis of the heart is directed towards the right lower quadrant of the heart, so it is between plus 90 to plus 180 degree, and it is right axis deviation. Last example here, lead 1 is negative and lead AVF is negative. So lead 1 is negative, it is directed toward 180 degree. Lead AVF is negative, it is directed toward minus 90 degree. If we merge these two images together, the axis of the heart is directed toward the right upper quadrant of the heart, so it is extreme axis deviation. So Quadrant method is the simplest method for determining the axis of the heart. It uses only lead 1 and lead AVF to determine whether the axis is normal axis, left axis, right axis, extreme axis. Now we are going to speak about another method, which is the three-lead method, and from its name we are going to add a third lead here, which is lead 2. But the question that would be raised in our mind, why? Why do we need a third lead? The answer is simple here, because the addition of lead 2 can help to determine pathological left axis deviation from normal axis, or something called physiological left axis deviation. What does that mean? Let's see an example. For example, if I use a Quadrant method for a patient who is having positive complex in lead 1 and in lead AVF, so we could know that it is positive or normal axis. But actually we don't have just simply 4 quadrants in order to apply the simplest method, which is the 4-quadrant method. We know that the normal axis is not between 0 to plus 90, it is from minus 30 to plus 90. So for example, this sector, which is represented by 120 degree, not just 90 degrees, is not simply or not literally a quadrant. And the left axis deviation is not simply between 0 and minus 90. No, it is between minus 30 to minus 90, so it is just a sector of 30 degrees. The right axis and the extreme axis is not a big deal, it is 90 degrees. So it is not actually 4 quadrant, just is an important fact in understanding the ECG axis. That's why we need three-lead method in many cases in order to precisely determine the axis of the heart. For example, if lead 1 is positive by Quadrant method, we could expect, for example, that if EVF also is positive, it is normal axis, and EVF is negative, so it is left axis. This is the simplest way, the Quadrant method. But in this way, the axis may be between 0 and minus 30, and it is still normal. Here, as we see from this dashed line here, that we need another lead to decide whether it is normal axis between 0 and 90 degree, or physiological left axis between 0 to minus 30 degree, or pathological left axis between minus 30 to minus 90 degree. So what we need to learn from this, that if the axis of the heart is between 0 to minus 30 degree, by the Quadrant method it would be determined as left axis deviation, but actually it is still normal, and we should only apply the word left axis deviation to axis between minus 30 to minus 90. So we need to put this image here in our minds. So let's apply this method in order to understand what we are saying now. For example, as we mentioned, that lead 2 is used as a third lead, and lead 3 and EVF also can both be used in the 3 lead analysis. So we can use lead 1, 2 and EVF, or we can use lead 1, 2 and 3. But in order to be much more simple here, we would use the first one, lead 1, 3 and EVF. So how we are going to apply this? We know, of course, an important rule that positive QRS in lead 1 would align the axis in its direction towards its positive pole. Positive QRS in lead 2 aligns the axis also in its direction. Positive QRS in lead EVF aligns the axis in its direction. So if lead 1 and 2 are both positive, sure the axis is between minus 30 and 90 degrees and plus 90 degree, and it is normal axis. So the issue is when only lead 1 is positive. This is the big deal. Let's apply this. For example, lead 1 here is predominantly positive, so it is directed towards its positive pole. It is directed towards 0 degree. Lead 2 is predominantly positive, so the axis is directed towards its positive pole at plus 60 degrees. And lead EVF also is positive, so the axis is directed toward plus 90 degree. So from the direction of these 3 axes, we could expect that the axis of the heart is between 0 degree to plus 90 degree, so this patient has normal axis from 0 to 90 degrees. Let's have another example. Lead 1 is predominantly positive, so the axis is directed towards 0 degree. Lead 2 is nearly predominantly positive, or it may be slightly equiphasic, but we are going to consider it as predominantly positive, so it is directed toward its positive pole at plus 60 degree, but lead EVF is predominantly negative, so sure it is not directed towards its positive pole, it is in the opposite direction toward minus 90 degrees. So here we can expect that the axis of the heart is between plus 60 degree to minus 90 degree, so we could expect here that this patient has physiological left axis deviation between 0 degree to minus 30 degree. So it is not left axis deviation, no, it is still can be normal, because lead 1 and lead 2 are both predominantly positive and EVF was negative. Let's have another example. Lead 1 is predominantly positive, lead 2 is predominantly negative, so here's lead 2 is negative, so the axis is directed away from the positive pole. It is nearly at minus, or we can consider like minus 120 degrees here at the right upper quadrant. And EVF is also predominantly negative, so it is directed toward minus 90 degrees. So the net overall direction would be directed toward the left axis deviation sector between minus 30 to minus 90 degrees. So here, in order to consider the patient to have left axis deviation, which is a pathological form, so we should have positive complex in lead 1 and negative complex in lead 2 and EVF in order to consider it as pure pathological left axis deviation. Let's have another example. Lead 1 is negative, lead 2 is positive, and lead EVF is positive. So here the net overall direction would be from plus 60 degree to 180 degrees. So sure it is right axis. So sure I have positive complex in lead 2 and lead EVF, and negative in lead 1. Sure it is simply right axis deviation. Last example here, lead 1 is negative, so it is directed toward 180 degree. Lead 2 is also negative, so it is directed towards the right upper quadrant at minus 190 degrees. AVF is also negative, so it is directed at minus 90 degrees, so sure it is an extreme axis deviation between minus 90 to 180 degree. So here we can consider that the three-lead method is used in order to differentiate normal axis and the physiological left axis deviation from pathological left axis deviation. So for example, the quadrant method and three-lead method would tell you the same information in case that the patient has right axis deviation or extreme axis deviation or normal axis between 0 and 90 degree. But the value of using the three-lead method is to differentiate the physiological left axis deviation, which is still normal axis, from pathological left axis deviation, which is a pure form of left axis deviation that should be separated from normal axis and from physiological left axis deviation. Equiphasic method, which is the last method to use in determining the QRS axis, depends on the value that if the QRS is positive in any lead, of course the axis directed toward its positive pole. And if the QRS is negative in any lead, so the axis is in the opposite direction towards its positive pole. And if it is equiphasic, it means that it is perpendicular to this lead. So let's see here, for example, the axis is perpendicular to the lead, showing the equiphasic complex. So if we use here, for example, this same diagram, we need to know what we are going to do in order to calculate the axis. The step one is to find the isoelectric lead. The isoelectric lead is the lead in which R wave amplitude is nearly equal to Q wave or S wave amplitude, so we cannot consider this lead to be predominantly positive or predominantly negative. No, it is nearly equiphasic. Or sometimes you may find lead in which the QRS is flat line with no discernible features or characterized feature in order to determine its axis, so we could consider this lead to be isoelectric lead. So for example, if lead 2 is equiphasic, as we see in this image that lead 2 nearly have equal amplitude of the Q wave and also of the R wave. So if lead 2 is here, so the axis of the heart is perpendicular to this axis, so it is directed either to minus 30 degree or to plus 150 degrees. So this is step 1 of the equiphasic method. Step 2 is to find the positive leads, because I told you that the axis is perpendicular to lead 2, but I don't know whether it is directed toward minus 30 or to plus 150. So I need to look for the lead with the tallest R wave or the largest RS ratio. So for example, if AVL was positive in this ECG and lead 3 was negative or predominantly negative, so I could expect that the axis of the heart is not just perpendicular to lead 2, but also it is directed towards the left upper quadrant, because AVL is positive and lead 3 is negative. So mostly it is directed towards minus 30 degree towards the positive pole of AVL, so the axis is minus 30 degree. So the equiphasic method is one of the methods that is going to give you like an estimate of the value of the axis, not just normal axis, left axis, right axis, extreme axis, but it could give you like an estimate of the value of the QRS axis. So the equiphasic method is the only method that determines the axis accurately by a value, not just a range. So we have ranged here in the methods for determining the axis from the Quadrant method, which was the simplest way that could be used by anyone in order to determine whether the patient has left, right, normal, or extreme axis. We use the three-lead method, which is much more accurate in order to differentiate the physiological from pathological left axis deviation, and the equiphasic method, which give you a value for the axis, not just a range. So let's see, for example, some ECGs in order to use any one of these methods to determine the axis. For example, here, the patient has positive complex in lead 1 and positive complex in AVF. If we use, of course, a quadrant method, it is simply normal axis. And if we apply here lead 2 was also positive, so if we use a three-lead method, it would be also normal axis. So here I have normal axis of ventricular depolarization. Here, for example, I have positive complex in lead 1 and negative in AVF. And also it is predominantly positive in lead 2. If I use the quadrant method, I would say that it is just left axis deviation, but as it is predominantly positive in lead 2, if I apply the three-lead method, it is not pathological left axis, it is normal axis, but it may be in the range of physiological left axis deviation from 0 to minus 30 degree, which is still in the range of normal axis, because as we mentioned before, it is not just 4 quadrants. No, we have 2 simple quadrant of the right axis deviation and the extreme axis deviation, and we have another sector which have like 120 degrees and the smaller sector for the left axis which have only 60 degrees. Here in this example we have positive complex in lead 1, negative in EVF, and also predominantly negative in lead 2. So if we apply the Quadrant method, I could say that this patient has left axis deviation, and also if I use a 3-lead method, it would give you the same value because the complex was negative in both EVF and in lead 2. Here, if I use here the same methods, for example, complex is predominantly negative in lead 1 and it is predominantly positive in EVF. So it is just simply right axis deviation by both the Quadrant method and as well as by the 3-lead methods. If we try to apply the Equiphasic method here, for example, if we are going to look for the lead with the equiphasic complex, we could say that it is EVR. EVR has R wave and Q waves of nearly equal amplitude. So I could expect that the axis here is perpendicular to AVR. So it is either directed, for example, between minus 30 degree to plus 120 degrees. And then I'm going to look for the positive complex. So for example, I have the tallest R wave here in AVF and also in lead 3, so I could expect that it would be directed towards the right lower quadrant of the heart, so I could estimate the value of about nearly plus 120 degrees. Here in this example we have lead EVR, as we mentioned, is equiphasic. So the axis is perpendicular, as we mentioned here, between minus 60 or plus 120 degrees. And as we mentioned here in the last example, that the complex is positive in lead 3, and this we can consider as the tallest R wave. So as we mentioned, the axis is plus 120 degrees. So in this ECG, I applied the Quadrant method. It gave me a value of right axis deviation because the complex was positive in lead 3 and lead 2, and lead 2 and AVF, and it was negative in lead 1. And we applied the Quadrant method, it would give me the same answer, and if we apply the Equiphasic method, it would give you a value of an axis of 120 degrees. So the last thing in our lecture today is that why should I know how to determine the QRS axis? As we mentioned in the start of this lecture, it helps you in diagnosis of fascicular blocks. It helps you to detect limb bleed reversal, which for example it would be positive in AVR and negative in lead 1 and AVL, and we are coming in another lecture to an example of limb bleed reversal. It helps electrophysiologists in localization of the origin of PVCs and help them as well in localization of the origin of VT, which is very important in ablation procedure in order to determine the origin, and so we are going to ablate this origin of this tachycardia to terminate them. So at the end of our lecture, we understand now the value of determining the axis of the electrical activity of the heart, and we understand the 3 different methods of identifying the axis of ventricular depolarization, because as we mentioned that we have 2 different axes in the heart. Thank you for your listening, and if you have any questions regarding this topic, because I know it is one of the difficult topics in ECG, please leave it in the comments below. Thank you very much.